So thank you very much, Nathan, for the introduction. And I'm very happy to give this overview of Mythic, which is a Python library for quantum error mitigation. So this library has been developed under the Unitary Fund organization. And this is a non-profit working in the field of quantum technology. And you can find more information in the website. And you can also check the previous talk of Sarah Kaiser. It was on Monday with more information on Unitary Fund and open source software. But now I'm going to focus on Mitiq. And all the people that you see here are the contributors of Mitiq. So a lot of people, some of them from Unitary Fund, but also external contributors. So I want to thank all of them. This is the GitHub link, and we also have a white paper related to this software library. This is very simple outline of this presentation. The first thing that I want to do is to give an overview of what is error mitigation. And after this, I will try to explain what is Mythic from an abstract point of view, from a general workflow point of view. And also we'll focus a bit on zero-noise extrapolation. And finally, I will, if there is time, I will give an example with a notebook. So let me start with quantum error mitigation. And actually, the way in which I want to explain this is using an analogy. So I want to use this idea of taking a picture of something, which in this case is the Leaning Tower of Pisa, but it could be any kind of object. And you assume that this is the ideal computation we want to do with a quantum computer. But unfortunately, we have NISQ devices, so some computers that are not perfect. There is noise. And because of this, the real result that you get is something that looks similar to a low-resolution image. And in order to solve this problem, actually, I'm not sure if it's easy to solve it at all, but a possible way in the long term is to apply quantum error correction. So quantum error correction implies that you add some expensive piece to your camera that allows you to take a better high-resolution picture. In a quantum language, it allows you to perform a computation such that the result that you get in the final measurements of the computation is has high fidelity with respect to the ideal computation. On the other hand, as I said, this is not very easy to apply at the moment with the devices that we have today. And what you can do instead is something which is called quantum error mitigation. If you take this analogy, you can think of quantum error mitigation as taking a lot of pictures of the same object, but from a different perspective. You change maybe the orientation, you change something in the way in which you do this photo. But all these photos that you see here are noisy. So they are all low resolution images. But if you take a lot of these, you extract maybe more information about the ideal computation that you want to do. And if you do a post-processing, you could be able to infer a better result. So an image in this case with a better resolution. So a bit more rigorously, these two methods are called, one is standard error correction. This is the well-established theory of error correction, which implies encoding logical qubits into many physical qubits. And it's scalable in principle, but unfortunately, it is very hard to apply with near-term quantum computers. And the second option that I've shown you is error mitigation, which from a quantum point of view implies having multiple and different noisy quantum computations, collecting the results, and doing a post-processing of this noisy data to extract a better estimation of expectation values. So this is asymptotically not scalable, but it is easy to apply with near-term quantum computers. And the idea of Mythic is to start implementing these techniques with the devices that we have today until we reach standard error correction. And the 2 points that you see here that characterize error mitigation is this fact of taking multiple and different noisy computations. That's the first thing to remember. The second thing is that you have to infer ideal expectation values from noisy data. And as I'm going to show you, these are the 2 main tasks that Mitiq is able to implement in your computations. So what is Mitiq? So Mitiq is a Python library that has exactly this scope of providing a toolkit to apply different error mitigation techniques in a way which should be easy for the user. It is compatible with many software libraries, Cirq, Qiskit, Rigetti, Bracket, Penny Lane, and it has a structure which is by construction backend independent, in the sense that we don't want to play with the details of the backend, but at the moment, Mitiq acts at a gate level. And I will explain later what this means. So to explain how Mitiq works, we can see how one typically use a quantum software library. For example, one of these software libraries that you see here on the left, to execute something on a backend. And the typical workflow is that you write down a quantum circuit, and then you send this to a backend, to the hardware, which executes the circuit, and from this you extract a noisy expectation value. Maybe you extract measurement shots, but what we are caring about in this talk is the evaluation of expectation values. And the scope of Mitiq is acting in the middle between the user and the hardware in the minimal, in the less invasive way as possible. So from the point of view of the user, using Mitiq should almost be equivalent to having a better hardware. What does it mean? It means that you still send a circuit to your mitigated hardware, and you get back an error mitigated expectation value, more or less mimic in the same way as if the hardware was better in some sense. And the way in which this is possible is to, with these 2 main tasks that Mitiq implements, that are the 2 tasks that I said to you before, which are at the basis of error mitigation. The first important point is to generate from a quantum circuit a set of intermediate circuits. So this step looks very similar to a compiler that takes a circuit and converts it into other circuits. But here we are generating not one, but a lot of different circuits. These are executed by the backend, and Mitiq doesn't want to know how the backend works. Mitiq just wants to know the results, these noisy results, and from this you can infer an estimation of the ideal expectation value. And so coming back to the previous analogy, what Mitiq does is basically taking a lot of pictures which are noisy, using a noisy backend, and extracting a post-processed image of the ideal computation. So Mitiq at the moment implements 3 error mitigation techniques: Zeronoise extrapolation, probabilistic, error cancellation, and Clifford data regression. And all these techniques are actually compatible with this workflow that I have just shown you. So the compilation of a quantum circuit into many circuits, execution, and post-processing. This is true for Zeronoise extrapolation, PEC, more or less also for CDR. In this talk, I will focus on zero-noise extrapolation, but maybe I can show something about PEC too in the final part of the talk. So what is zero-noise extrapolation? So the main idea could be summarized by this meme that we made, which is why struggling to reduce the noise if you can increase the noise. So reducing the noise is very difficult. And that's the main problem that we have today with quantum computers. And maybe it is easier, and of course it is actually easier to increase the noise. On the other hand, it's not clear how increasing the noise may help you to get a better estimate. It seems quite counterintuitive. But to see how this is a possible strategy, we can check this plot that you see here on the right, in which we are plotting an expectation value as a function of the noise level. And the noise level is normalized such that when lambda, this parameter, which is called noise scale factor, when this is equal to 1, we are evaluating an expectation value at the hardware level, the minimum noise that you can have in your quantum computer. And unfortunately, we cannot go below, but what you can do is you can measure the same observable with the same ideal unitary that you want to implement at a higher level of the noise. And so you start collecting more points in this graph. And once you have all these points, maybe you can fit a model to your data and such that you can get some kind of extrapolation to the zero noise limit. Typically, you fit a polynomial or you can fit an exponential to your data. And this is how the zero noise limit of the expectation value is estimated. So coming back to the pictures of the leaning tower, basically zero noise extrapolation works by taking the ideal circuit, applying noise scaling at different levels of the noise. I'm not sure if you can see that here, these pictures are more and more noisy. And from this, you can extrapolate what is the error mitigated result. And then the question is, how can you increase the noise of a quantum computation? And if we come back to the usual analogy, a way to increase the noise is to maybe increase the distance from which you take the picture. This is what you can do if you take a photo of an object. From a quantum point of view, it turns out that you can do something very similar to this, which is increasing the depth of a quantum circuit, artificially increasing the depth of a quantum circuit. So there are different ways of doing this, and actually one of the most important ways is called pulse stretching. And the idea is the following. You have a quantum circuit which contains several gates, and all these gates, from a physical point of view, corresponds to Hamiltonian pulses that are used to control the qubits. Now, if you stretch in time the pulses, you can effectively reproduce the same circuit, but in a longer amount of time. And because of this, if you execute this on an ideal device, you get exactly the same result of this. But if you execute these two circuits on a noisy device, you are effectively increasing the level of noise because you have a longer computation, and so the probability of getting an error increases. And another way of doing this is at a gate level. And actually, this is what Mythic does. Instead of acting at the level of pulses, you can do this in what we call digital noise scaling. And it's basically consists of replacing gates or group of gates G with G dagger G. So let's look at this method, which is called local folding, for example. You take a circuit, and for each gate, you apply G dagger G. In this way, since G dagger G is equal to the identity, you are not changing the unitary of the circuit associated to the circuit, but you are changing the depth. You are increasing the number of gates. The same trick can be applied globally to the full circuit. This is called global folding. And again, the unitary with an ideal backend is the same, but the depth with a real device implies an increase of the noise. So this is basically a way to get more noisy computations. And this is just an example of how one could use Mythic to increase the depth of a circuit. So you get, in this example, a Qiskit circuit, which is composed of two gates, the Hadamard and a control node. And then once you define this circuit, you import from Mythic a noise scaling function, which is, in this example, fold global. You apply the function to the circuit, and you get a circuit which is in principle equivalent to the original one, but it has a larger amount of gates, and so it is subject to a larger amount of noise. And this is for noise scaling. How can you do the fit? How can you extrapolate to the zero noise limit? Also, in this case, there are a lot of possibilities. You could do a linear fit, a polynomial interpolation, polynomial fit, an exponential fit, and also adaptive strategies could be implemented in which you measure expectation values and you choose the next noise level depending on the result that you got. And these are all built in Mythic, but you could also define your custom extrapolation method. And basically, this is the extrapolation method is summarized by an object that we call factories. And maybe later I will show you how to use those. So this is an overview of zero noise extrapolation. I just want to say a few words about probabilistic error cancellation, which is apparently a quite different technique. It is based on sampling from quasi-probability distributions and taking linear combination of circuits and so on. But from a practical point of view, the workflow is very, very similar to what you have seen before. You get a circuit, you sample a series of circuits from this quasi-probability distribution. I cannot go into the details now, but it's a series of circuits such that their linear combination reproduce the ideal result. If you go back to the analogy of pictures and photos, you can think of measuring different components, maybe color components of the pictures, such that when you combine them, you get to the mitigated result. I won't say more about this because I want to use the last minutes of this talk to give you an example with a Jupyter notebook. And hopefully I can do this now. Let me see. Can I share again my screen?
Go for it, Andrea. I'll cover for you. You're clear.
Okay, sorry.
No worries, Andrea.
Okay.
Andrea's just pulling up his Jupyter notebook for us. Make sure to get those questions in the chat for Andrea. I saw a few coming in already.
So I think I'm sharing the notebook, but I'm not sure if you can see it. Okay.
All right. Go for it, Andrea.
Okay, so in this notebook, I will try to show how to use Mythic. And since this is an hackathon organized by Xanadu and also by people from Penny Lane. I will try to use Penny Lane, but as I said before, this is compatible with a lot of software libraries. So what I want to show you is how to compute these three steps: how to compute an unmitigated expectation value, how to apply zero noise extrapolation, and if we have more time, maybe I can show you how to apply probabilistic error cancellation. So let's consider the typical situation in which you are using maybe Penny Lane to evaluate an expectation value. So usually you import Penny Lane as a library, and then you define a circuit. Actually, you define you set the number of qubits, in this case 4. And since we want to simulate the effect of noise and the mitigation of this noise, we initialize a noise model, which is a depolarizing channel of some given noise strength. And also, we initialize an ideal backend without noise and a noisy backend with depolarizing noise. And with this, we can start to define a circuit. And of course, usually you have a meaningful circuit, but in this case, we just want to show how error mitigation works. So we define basically a random circuit, which can be done with this basically template that you already have in Penny Lane. It's a variational circuit with random gates. And so when you use this template and you actually apply after the template the inverse of it, such that it's a random circuit which is equivalent to the identity, you can also measure an expectation value, in this case, the Pauli Z to the qubit 0 expectation value. And as usual in Penny Lane, you define this as a Q node. I don't go into the details because probably you know this better than me. But once you initialize these Q nodes, you have an object that represents a computation, so a circuit with an expectation value. And also, you have an object that, given some variational parameters, returns you the expectation value. So since the circuit in this case is equivalent to the identity, the ideal expectation value is 1. But because of noise, if you run the noisy Q node, you get a result which is a bit different, 0.91. And so if you take the absolute error, this is the bias that the noise is introducing in your computation. And the idea of Mythic is trying to reduce this noise. So let's see how we can reduce this noise in the simplest way as possible in Penny Lane. And actually, this can be done in 3 steps. These steps are importing a noise scaling method for Mitiq, importing an extrapolation method, and also using a mitigate with ZNE transform, which is an object that you have in Penny Lane. So this is very simple. So you import from Mitiq ZNE scaling a noise scaling method. And this is something that you can take directly from Mitiq. For example, fault global is one of the noise scaling methods that I've shown you before. But maybe you could also define your own custom way of scaling the noise. Also, from Mitiq, you can choose an inference method. In this case, we can choose Richardson extrapolation, and you can set the scale factors. And once you have done this, what you can do is you can take this mitigate with ZNE, which is a transform in Penny Lane, to map your noisy Q node to a mitigated Q node. Basically, when you do this, you get a mitigated Q node object that automatically returns an expectation value, which is error mitigated. And as you can see, the error without error mitigation was this. The error with zero noise extrapolation is this one, which is much better more accurate. So an important point here is that this method is optimized for penny lane. However, there is a more general way of using Mythic, which is independent on the software libraries that you are using. And so I think I still have maybe a few minutes. I will try to show this. It doesn't take too much. So basically, this method, as I said, works with different techniques, with different software libraries. But since we are using penny lane, we need to represent a circuit in a way which is compatible with penny lane. And in penny lane, the closest analog to a circuit is called a quantum tape. And what we do, we just take this template that we used before, and we define it as a tape. It gives you exactly the same kind of gates, but as you can see, there is no measurement here. It's just a set of operations. And then if you want to use this tape to evaluate expectation values, you can use, as we did before, quantum nodes. So you take that, you define an ideal node and a noisy node implicitly using a quantum tape gates that you defined before, and you wrap them into a quantum node. And these are exactly the same result that I've shown you before, but now they are evaluated starting from a quantum tape. And if you have this, the final step is defining a Mitiq compatible executor. So this is a function that takes a quantum tape or a circuit and returns an expectation value. Actually, this is very simple because what you have to do is to take just this quantum node that we define now, and you can just wrap it into a function that returns the expectation value. So basically, now when you call this function execute, you take a tape and get the expectation value. When you have this, basically applying zero-noise extrapolation works in the same simple way as we have shown before. You define a noise scaling method, an inference method, and what you mitigate now is the executor. So this function is a noisy executor of a tape, and with this mitigate executor function that you have in Mitiq, you can get a mitigated executor function that takes a tape and returns a mitigated expectation value. So this method is a bit more general. For example, allows you to see the extrapolation fit, to get all the history of the measured expectation values, and so on. And what is more, since we have this executor, it is very easy to switch to different error mitigation techniques. For example, if you import the submodule of Mitiq, which is called PEC, you can apply in exactly the same way, with exactly the same workflow, also a probabilistic error cancellation, which is a completely different technique, but still allows you to improve the error of the quantum computation. So this was a very quick, maybe a bit superficial notebook, but hopefully this was enough to give you an overview, an idea of how to use Mitiq. And now maybe I think that's it. I have just a final slide with the conclusions, but I don't know if I can stop sharing here and going to the other slide. Maybe I can.
Go for it, Andrea.
Okay, I will do it.
Well, Andrea is pulling up his final slide. Reminder to send those questions in the chat, and we will get them to him in a few minutes. Well, also a reminder, we will be having a raffle at the end of Andrea's talk, so stick around for that.
Okay. Yeah, so I think the conclusions of this talk is that hopefully gave an overview of what is error mitigation in general, how it can be applied with Mitiq, and I also shown you some examples using a notebook to show how to use it in practice. What can we do in the future? Hopefully, we can support more error mitigation techniques in Mitiq, and benchmarking error mitigation techniques is quite important. And of course, there is a lot of scientific research to do in this field. It's not clear at all what technique is better, what is the scaling, if there are other methods to mitigate errors which are better, and so on. So this is a very new and active research field. And with this, I think I thank you for the attention, and I'm waiting for questions.
Great. Amazing. Thank you so much, Andrea. Let's get those questions in the chat for Andrea. First thing, I want to ask a question for you, Andrea. You told me that you are the person who actually picked the name Mitiq. Is that right?
Yeah, that's true. That's true, yes. And I hope it's clear that it comes from mitigation. And if you just change a little bit the G, it becomes a Q. And as usual, there is a Q in a lot of quantum
there has to be a Q.
libraries. Maybe it's becoming a bit boring, but that's the Q.
So you've actually been part of the Mythic project from very early days. I'm curious, at that stage, Unitary Fund was known for its microgrant program. Why get into creating a new open source library, and specifically why error mitigation?
Yeah, exactly. So the initial activity of Unitary Fund was this microgrant program, which is still active. Feel free to have a look and apply if you're interested in this. But why Mythic? I think what we are trying to do is to act with Unitary Fund in two directions. One is helping the ecosystem with these microgrants, with this creation of a community related to quantum information and quantum computing. On the other hand, we try to develop our own research and our own software tools. And basically, at the moment, this is our main software activity. We also have another one, which is Metric, to benchmark different devices and techniques and computers.
Also with a Q, right?
Also with a Q, exactly. Very similar name. And but why Mythic? Because we think that error mitigation is something which is important for everyone. So it's not a very specific application of quantum computing. It's not focused on a specific device, but it is more something that all devices, all software platforms, all people doing research and applications in quantum computing need in order to improve the results. And so this is maybe something good for an open source and also for a non-profit organization like Unitary Fund.
Awesome. So Andrea, these days you're working a lot on software and research related to software. But I heard that you used to be quite the strong experimentalist back in the day, back in your master's days. Could you kind of tell us, why didn't you stick with the experimental side of things? Why did you end up becoming a theorist?
Yeah, so I think this is related to the story that I told you about this, that I've written actually. Is back days when I was doing my master's, I did an exchange program. So in Europe, it's called Erasmus. When you study in one country, you do a few months in a different country, and you do classes in a different country. And it was for me an experience in the UK, and there was this experimental, I think, classical optics class. And so it was an exam in which you have to make experiments and make a report. And the task was to now that I remember, was like measuring the wavelength of a laser using interference experiment. And the result, that this experiment was very, very difficult. The results were very, very hard to achieve. And basically, we took the measurements in the lab, and at home, we had to post-process these measurements to get this wavelength of the laser. And it was very, like, an order of magnitude far away from this. We really didn't know how to do it. And I think I did the worst thing that you can do if you are working on as a scientist and as a physicist, which is creating fake data to get the result that you want. And so this is not very nice to say, but this is what I did. And actually, the most embarrassing part of this was that we were actually in two Italians that were doing the same Erasmus. And the professor said, "Oh, these two Italian Erasmus guys did the best experiment in this class." And this was a bit, I was a bit ashamed of this, but in the end, maybe this was the moment in which I decided not to work.
Career choice was made for you.
Exactly, not as an experimental physicist. By the way, from a theory point of view, it was not easy to make fake data in that experiment.
So you still had to work at it.
Like a reverse engineering of the problem. It was not easy.
All right, folks, don't do what Andrea did.
Exactly, don't do it.
Cool. Andrea, you told me that you're actually experimenting with a 4-day work week. You only work 4 days per week. You're still here with us. You still have a job. Tell us how it's going.
Yeah, that's an experiment that I'm doing. So actually, I have to say that I don't always respect this, but officially I'm a kind of part-time position in which on Monday I'm free to do not to work. Basically, it's a 4-day week job, and I started in this way basically just by chance, because the position initially was part-time. But actually, I like it a lot because it allows you to do a lot of things, not just, basically two big reasons. One is I have more time for my family and for my children and all these family-related things. But also you have some time to work with a free mind on whatever things you have in mind. Usually when you start doing research on thinking about research ideas during the work time, you feel a bit guilty. Maybe you feel that you are losing time, and having a day in which you are completely free, even from your job, I think it's very, very helpful for this. So actually, I'm not saying that that the 4-day week should be the standard for all people, but for sure it's something to do experiment on it. So
you'd recommend it to others to try it.
Yeah, and maybe even as a kind of let's say social point of view, we have a 5-day week. Why not 6 and why not 4? So things could change in the future, and nobody knows.
Fair enough. All right, Andrea, we got lots of great questions from the chat. If you don't mind, let's jump over to some questions from the audience.
Yes.
All right, so there's a couple of questions here. Maybe I'll just pick one that's on the same topic, but this is from Heisenberg's dog. Any comments on the cost overhead associated with these error mitigation techniques and how it scales?
Yes. So there is a cost, and the cost is, for example, is very clear here. Let me take this. So, for example, this is an experiment in which you have a randomized benchmarking circuit where the ideal result is 1. This is the ideal expectation value. But because of noise, you get this. And what you can do is to take more measurements such that you can do this zero-noise extrapolation for it. And so already from this plot, you see that to estimate this expectation value, you are measuring a lot of noisy data. So this has a cost. And what is more, because you are extrapolating, it is, even from a graphical point of view, clear that if you have some noise, some error bars on these points, this will be amplified when you do the extrapolation. And so you have an extra cost in terms of sampling. So the sampling cost to achieve a given amount of accuracy increases. And there are rigorous ways to estimate this sampling cost. And yeah, without going into the details, a simple way to estimate this is to look at the coefficients which are related to the linear combination of expectation values that gives you the ideal expectation value. Most error mitigation techniques are based on linear combination of noisy results. And basically, the one norm of these coefficients provides you how much sampling cost you have to pay to apply error mitigation. I don't know if it was clear, but
Sure thing.
if necessary, we can go more into the details, but I think that's the main message.
Thank you very much. Maybe we'll jump into another question then. So question from Shulok. Can Mitiq use multiple techniques simultaneously? For instance, the probabilistic error cancellation and zero-noise extrapolation.
Yeah, that's a good question. In principle, yes, and we are trying to test this kind of combinations. And the basic message is that, as I've shown you before in the notebook, what you can do with Mythic is to create an executor, which is basically a black box that takes circuits and gives you back expectation values, which is error mitigated. So it means that instead of having your hardware, which is unmitigated, you have a black box which behaves as an hardware which is error mitigated. And that's what we called this mitigated executor. But now you can apply another layer of error mitigation on top of this. Basically, you can mitigate a mitigated executor with a different technique. In this way, you are basically stacking more error mitigation techniques, one on top of another one. But the main question is this helpful or not? It's more a research question. From a practical point of view, Mitiq allows to do this in a very easy way.
And when you do this, I guess one question I always had with the error mitigation is that the final result that you get, the mitigated result, how physical is that? I think I saw in your example, your expectation value was 1.02, when I know that the maximum expectation value would be 1, right? So how do you kind of constrain things to be physical if you're mitigating?
Yeah, so you could try to enforce physical constraints on the error mitigation inference that you use. On the other hand, this happens very often in quantum experiments. For example, if you do quantum state tomography, sometimes you get a state which is not completely positive, or sometimes you get a state which doesn't have trace 1. And what is important is that you want to estimate a quantity with a good level of accuracy. And maybe you end up with error bars a bit beyond the physical regime. But still, if you are maybe doing a VQE experiment, or if you are applying any variational quantum algorithm or near-term quantum algorithm, it's not so important that the result deviates from the physical boundaries of the possible outcome. you get expectation value of Z, which is 1.001, still okay for most of the algorithms.
Okay, so it's important that it's close, but it doesn't necessarily have to be
Exactly.
physical. Cool. There's lots of great questions here. I'll see if I can pull out a few more. So it's a question from Lord Ortega. It says, do you think you could use something like a quantum or generative adversarial network for error mitigation in the same way they're used with deblurring images? So maybe some sort of like machine learning model or some other model for doing error mitigation.
Yeah, so I'm not sure about adversarial networks, but for sure there is a lot of research on applying machine learning techniques for doing error mitigation. And actually, one of the techniques that we have in Mythic is called Clifford data regression. This was developed by the group of Los Alamos, quantum information group of Los Alamos. And the technique is based on very machine learning inspired approach, in which you take circuits and you map them to near Clifford approximations, so circuits that can be simulated efficiently on a classical computer. And in this way, you can train your model. You can train a statistical inference model by comparing the results that you get on the hardware and on a classical computer. In this way, you can later use your trained model to get better expectation value. And I guess that in a very similar way, you could use an adversarial approach, machine learning adversarial network, but also in this case, you typically need to train the model, you typically need to know to use circuits for which you know the result.
That's right.
And there are different ways of doing this. Maybe using circuits which are used just for the training, or maybe applying approximations of your circuit, for example, using Clifford gates and Clifford operations that are efficiently simulable on a classical device.
Great. Lots of amazing questions, lots of amazing answers from Andrea. Andrea, unfortunately, we are out of time. It's been really great to have you on today talking about Mitiq. Thank you so much for joining us.
Thank you very much for inviting me.